So with that in mind, the last missing tool for us is uniqueness, and we want to prove this. And you could think of it as a little bit analogous to the issue that we had for Taylor series, except that this is middle and reverse. But if you have two Taylor series, power series that are the same, then this is the same as saying that the coefficients are the same. So this was discussed in a different setting, and the tools were quite different as well, but it's analogous to that. So you want to go from the terms being the same to the series being the same, or the functions being the same, to having the same coefficients. Okay, so let's state this theorem, the last missing piece. So f hat n is equal to an, which was defined as the integral of f theta e to the minus I n theta d theta. So this is the inner product of f with e to the en. So the nth basis element. And we suppose you have two continuous functions that are 2π periodic. If the Fourier coefficients are the same, then the functions are the same. So the Fourier coefficients uniquely determine the continuous function. And this is a remarkable thing, actually, in and of itself. Because if you think, what is the data? So what do you need to specify a continuous function on the circle? Well, and here what I'm thinking is that this 2π periodic function, because it's 2π periodic, it attains the same values at the endpoint, and after that it just repeats. So it's a more convenient way of expressing or thinking of the function, more geometric way, is to wrap up that interval and close it into a circle and think you're going around the same circle instead of going along the line. So we really can think of this function as a circle, as a function on a circle. And if such a function on a circle, you'd need to specify all of its function values. I mean, somehow none of these seem to communicate much with each other. However, what this is saying is that this function is uniquely determined by its Fourier coefficients, and these are a discrete function, a function on integers. For every n, it gives the Fourier coefficient. So somehow there's some connection between the circle and the integers. And this is something very profound. It's related to it's a form of duality, and it's called, in some instances, it's called Poincare duality. So, I mean, it's far beyond the capacity of this class to discuss this further, but there's some connection between continuous functions on a circle and the integers. And this idea is actually rather powerful. So this uniqueness statement is quite interesting. Okay, so let's try to prove this uniqueness statement. And one of the tools is something we didn't really use so far, namely density of functions, and a version of Weierstrass theorem. Well, we never really proved Weierstrass except gave a sketch for neural networks, but I did state a version of it, and I'll state here a slight variant of that version that is easier for us to use. So if we look at the functions from R to C that are complex polynomials, complex trigonometric polynomials. So what does that mean? They are an times e to the in theta for some an. So there exists a capital N, there exists a1, a minus n, up to an coefficients. And these can all be complex numbers. There's no restrictions on them. And a theorem of Weierstrass, and some aspects of this are due to Bishop. Usually Weierstrass theorem concerns only polynomials, but it's the same idea there. what does it state? It says that any function that we have, any continuous function, okay, here we will need 2 pi periodic, that's one of the modifications, can be approximated by one of these functions. So it looks like one of them in the following sense, that if you fix an error, epsilon, you can find a trigonometric polynomial that is close to f. So f minus g norm, which is the largest distance between elements, is less than epsilon. And I mean, if you want, you can equivalently state this as for every x in, or for every theta in R, we have that f of theta minus g of theta is less than epsilon. So we have our 2 pi periodic function. It's enough to look at some restriction of that. This is our f. Then there's some trigonometric polynomial that is very close to it. This theorem, it doesn't say anything about what the polynomial looks like. I mean, ideally, we'd like to say that this polynomial is actually a Fourier series or a part of the Fourier series, but that we can't say that, not with these tools. There are other ways of actually getting that, but here we're just saying that there's some way of approximating that. So now we will see actually why you would care about such a thing and how can it be used for things. So we need that tool. And another tool is that we need to say when a function, we will use this tool to estimate some integral. And well, there's a reason why I look at the square integral that's more deep, that's related to other tools that come from this inner product structure. So this should be really thought of as something like 2 pi times f inner product with f squared. So that's why these inner products are really natural in this context, and that's why we're looking at the square integral. But what we are interested in is that if you have a function whose square integral is 0, and that is continuous, and 2 pi periodic, then the function actually has to equal 0 everywhere. So the integral being 0 implies that the function is equal to 0. Now, to understand this proof and to understand this fact, you have to remember that there's one fake counterexample to this statement. So the fake counterexample is, I mean, I'll not draw it as periodic function, but let's say it's from 0 to 2 pi, it looks like this. And at pi, it jumps to 1, and then otherwise it's 0. So this function g has integral g squared is equal to 0, because the only point where it's not equal to 0 is at pi. So the upper Riemann sums are 0, the lower Riemann sums are all 0. So the Riemann integral is equal to 0, but the function is not 0, because at pi it's not 0. So where is the exception? Well, g is not continuous. So focusing on that example, I mean, let's see what is different for continuous functions and what makes this proof run. Well, the difference is that if you can have isolated points where the function jumps. You can make it a little bit worse than that, but I don't want to get into that now. But a continuous function, if it has a point where you're some value c, then by continuity, if you say look at c over 2 and 3c over 2, and suppose the function is positive, then there's a box that contains the graph of the function, or part of the graph of the function. Now, if you consider this part here, that will give you a positive area, especially once you square it, because then everything will be on the positive axis. So the integral can't be 0 because there's this little slab that is bounding it from below. Whereas for discontinuous functions, you can't create that slab. So this behavior is exactly kind of what's distinguishing continuity versus not continuity and why that assumption is there. Okay. So yeah, if we have time at the end, I will return to this proof a little bit, but for now, I will not do this proof because it's written in the notes carefully. With this observation in mind, I think you should be able to understand it. But if we have time, I will return to that at the end. So okay, then we have that fact. Don't worry, I'll remind you of these facts once things come up. And these are also on Canvas Wire, so if you want to scroll back and forth. But now let's return to our uniqueness theorem. It will follow from these two facts that we've stated, plus other tools such as orthogonality. So suppose you have two functions that are 2-pi periodic continuous with the same Fourier coefficient, and I want to say that the functions are the same.